What?
I get notifications when you and Killian begin recording, which is why I was absolutely laughing my head off a couple of weeks ago when Jan started OR without me, 5 minutes late, and he pops into the frame and goes, "Hi, John." Killian, does he actually watch these or not? I don't think so, but
Probably not. Right. Let's get on with it. We've got some things to cover. As a reminder, what we did yesterday, we talked about normal subgroups, and we proved that these three conditions are equivalent for a subgroup H of any group G. Well, the first condition tells you that the left cosets are exactly the same sets as the right cosets. And then there is, this one is the kind of auxiliary condition, and the second one, which is equivalent with it, is that you take the subgroup and any element of G, and you take all the elements that have the form of sort of G little h, G inverse, and H cycles through all the elements of the subgroup, you get exactly the same. Okay? And this is not true for all subgroups. This is true exactly when the cosets are the same, and such a subgroup is called a normal subgroup of G, so that's what we did as a reminder. And we saw some examples of normal subgroups, and then we had this theorem. Well, this theorem, it's a theorem definition, which says that.
That's when I got lost because I wrote factor groups and then I was paying attention and then it came down and then I got confused.
But everything I wrote, you can download from the okay, so what does this do? This defines. So you've got. I should really. I mean, I probably shouldn't draw pictures. Pictures will only confuse it. But what you're doing is, so the elements of a group can be anything, and we've seen they can be numbers, they can be permutations, they can be many other things. And in this case, the elements of a group are sets. Not just any odd sets, but they're the cosets of n, which is normal subgroup of G. So what you have is an operation that operates on sets. Like some operations that operate on sets. For example, union of sets. Okay, takes two sets, gives you another set. Section of sets takes two sets, gives you another set. And so here you have multiplication of sets. Takes two sets that have to be cosets, all then, and then gives you another coset of them. And we prove that if the subgroup that you start with, that gives you the cosets, is a normal subgroup, then this operation on the cosets forms a group. The multiplication somehow is inherited from the original multiplication of that group. So we proved this. What we didn't do, and what we should do now, is to actually look at some examples so that this abstract theorem receives some meaning in your mind. So let's do that now. Are you watching it live?
no. Yes, technically I am. Not been
Okay, so example 10.5 really is example 10.2 from yesterday, continued. And what was example 10.2? It was the normal subgroup of S3, which was the identity, the 3 cycle 1, 2, 3, and the 3 cycle 1, 3, 2. It's a subgroup. And they're inverses of each other, and you can check that it's normal because the cosets are the same. That's what we did. Now, what happens if you take S3 factor group, sometimes it's called quotient group, by n? So first of all, what is the order going to be? What is?
I just don't like the word confused.
Yeah, that's fair enough, but that's the word that everybody in the world uses, so we're better stick to it.
With bigness now. What's the bigness of S3 over N?
Bigness. I thought you were saying big mess.
You left the eye on last night. It hasn't known.
As opposed to order. Anyway, so when you recall the theorem, or if you look at it again, it tells you the order of the factor group as the index of the subgroup which by some previous theorem is just the ratio of the orders, and S3 has order notes all permutations of 3 elements, symmetric group, so 3 factorial, which is 6, and n you can count has 3 elements, so it's going to be 2. So what do you expect this quotient group or factor group to be?
Yeah,
Well, there aren't so many groups on, well, there are infinitely many, of course, groups on order 2, but they're all isomorphic to Z2. Only really just one non-isomorphic group. So this one, if I write the Cayley table, the cosets, as we saw yesterday, or even before, I think, are n and 1, 2, n. So you get n times n is n, because take 2 elements from n, you get an element from n. And this n is the identity, well, and this can't be anything else than n. Okay, so this group, S3 by n, is isomorphic to Z2. And in fact, it's isomorphic in a sort of a straightforward way. So when you look at this, this coset n contains all even permutations. And coset 1, 2, n contains all odd permutations. So what this really does, what it's telling you, is that if you take 2 even permutations, 1 from each coset, you get an even permutation. You get 2 odd permutations, you get an even permutation when you multiply them. When you get an even and an odd permutation, and no matter what order, you always get an odd permutation. And this is the meaning of the selectorization. So, kind of simplified, sort of. This is what it means. So, in fact, you could do this with the higher symmetric groups. You took the alternating group as its subgroup, It's a normal subgroup for any n instead of 3. And you get Z2 as, in the same way, the odd permutations, the even permutations as a coset is the identity of this factor group. And the second element is the odd permutations.
Yeah, sorry.
Is that amazing or confusing?
Both.
Anyway, that's example 10.
Sorry.
So this example really captures the parity of permutation. What's next? Example 10.6. Okay, so let's take the group Z with addition. Is that abelian?
Yes.
Yeah, addition of integers is abelian. And Z is n is any. So think 3. Okay, so these are all the multiples of n, integer multiples. So that's a subgroup, because if you add 2 multiples of n, you get a multiple of n. It's closed, and the 0 is there. And I mentioned yesterday that by exercise 10, any subgroup of an abelian group is normal. Okay, so also NZ is normal in NZ. What are the cosets? You've seen this before. It's just a matter of remembering.
N.
Now, the remainder class is modulo n. So you've got everything that's 0 plus a multiple of n, got everything that's 1 plus a multiple of n, 2 plus a multiple of n. Last one is n minus 1. You can do the cosets. Okay.
Okay.
So what's the factor group going to be? Well, you can take, so what the factor group is, its elements are the cosets. So in there, we do things like 1 plus nz. You want to add it with 2 plus nz. Okay, this is the all the integers that are 1 modulo n, all the integers that are 2 modulo n. You take these two sets and you add them. And you actually, what you do, you can add them element by element. So you can take any element there and any element there and add them, create a huge set.
and you get 3 plus nz. Well, if n is greater than 3. If n is 3, then you get 0 plus nz because you get factors of 0. But if n is greater than 3, then you get 3. So somehow it works the same as the addition of integers. There's this exactly what I said. So if you want to reach n, you have to go back to 0. So it's the same as addition of integers. Well, not the same, because the elements are the process, but otherwise it's the same as addition of the line. Okay, so this group is not the same, but it's isomorphic to, I think we called it Zn. Yeah, do you agree? You have no other reason, no other option than to agree. So that's an example of factorization works.
You get a subgroup. And the subgroup really, in some sense, the subgroup, the normal subgroup tells you all these elements are the same because they're all going to be the identity. So it's a bit like when we do addition of integers, but whenever we have 2 elements in a set, then we think that they're the same. So that's kind of what factor groups do. It's the same with the permutations when you think about it. Well, we do composition of permutations, but whenever we get to odd ones, we sort of consider them the same thing. And whenever we get to even ones, we consider them the same thing. And that's the factor group. You still following, or are you all asleep? No, I don't know. Should I do this one? I'm a bit scared of it because. Okay, I'll do it. So it's 10.7. Look at the dihedral group. So these are the symmetries of an n-gon. And the n is generated by 2 elements. One of them is S, which is vertical axis. What's it called? Symmetry. No. Reflection. Yeah, reflection is the right word. So that's the reflection. And then there's a basic rotation by 1 vertex, like 1 notch, as it were. And you get that the quantities that r to the n, if you rotate it n times around the whole circle, you get the identity, which is the symmetry. If you reflect it along the axis twice, you also get the identity. And one of the important ones is if you symmetry, well, if you reflect, rotate, and reflect again, I should have written it in the backwards order, but it doesn't matter, then you get, say,
All but 10 minus 1.
yeah, or R inverse, same thing. Yeah, just like rotating in the other direction. or in the other sense. Okay, so when you only combine rotations, you get a subgroup, a cyclic subgroup. Generated by basic rotation. Is this normal? I mean, is it a normal subgroup? Not, is this a normal subgroup?
Rotation is just abelian.
No, it's not abelian. The dihedral group is not abelian. There are two things. Well, first of all, you can use this. Okay, so when you think of the theorem, it says that what you want to check is if this is true. Okay. Well, you should check it for any element instead of the S of the group, but really, if you only check it for S, that's enough. Because if what you do here is a rotation, some sort of rotation there, then that is Rn. And, so there are not really so many elements for which. But this is the key. Okay, so this. Okay. So in fact, what you want, I'll be more precise then. So if you want to show that that Rn is a normal subgroup, you want that if you do G, Rn, G inverse, then you always get something at a rotation. Okay? For any G in the group. Sorry? Yes.
Does that make it more?
So if G is in Rn, then obviously G, Rn, G inverse, subset of Rn, because you're just taking elements of Rn, so you can't get out. It's a subgroup. If G is this, that's the key question. Well, first S inverse is S, and S times some rotation times S is a rotation. So that is true. And if G is the product of some rotations and some reflections, then you can kind of
So it is more.
so it is normal. In fact, I think I mentioned yesterday that any subgroup of index 2 is normal. So when you get exactly half the elements that forms a subgroup, then
In fact, any subgroup of index 2 is normal.
try to prove it on your own as an exercise.
You put that as an exercise 10.
Did I?
Yeah, you said it's part of exercise 10.
So what was that? Any subgroup of an abelian group? That's not exercise 10 then. Okay, so I confused it. Sorry. But anyway, both statements are true. In an abelian, any subgroup that's kind of obvious because maybe I even proved it yesterday. That's clear. Anyway, let's go on. Let's go on with this.
Yeah.
So the cosets doesn't matter whether they're left or right cosets because they're the same because it's normal. So of course one of them is the subgroup itself, and then there's another one where you reflect. Okay, and this is starting to be boring because again you get the two. So again you kind of say, well, if I'm only doing rotations, then that's one element, one coset, it's all the rotations. And the other coset is all the rotations where you flip. Okay, so all the symmetries where you flip. And if you only rotate, no matter how you compose it, you only rotate. You rotate and flip. And then again, we go back to rotations. So it's, again, some sort of parity on it, whether reflection is present or not. Okay, and that's not very interesting because everything I've shown you so far is there too. But got an extra example, which is not in the book, or at least not in this chapter. In fact, it's example 11.6. Okay, what we take is the general linear group, 3 by 3 invertible matrices over the reals. Okay, and it has a subgroup which is the special linear group. What are they? Do you remember? Special linear. One. Okay, so these are, this is the subgroup of all matrices whose determinant is 1, and these are the non-zero determinant matrices.
Oh.
0 you can't invert, and therefore when you're multiplying them, you don't want them in the group. Okay. Now, I promise you that this is normal.
I promise that it's an answer.
Well, I write what I say. And
I can't do that in the example, literally.
Yeah, I promise.
Prove it, I promise. I don't know you, I'll do it later.
but,
I owe you.
in fact, you'll see how to prove it in example 11.6 when we get there. So then all the pieces will have to stop. Okay. For now, just trust me that it's normal. And so do you remember, I think we were talking about this in one of the Friday tutorials, what the cosets are.
Oh, yeah, that's stupid. That doesn't narrow it down, does it?
Yeah.
What were they? Okay, so one of the cosets is SL3 itself, that's always. Do you have it? What did it say?
No,
No,
something else.
Okay, something else. Well, it would be better if you found this. In
Okay,
fact.
I don't have this in my notes.
Okay.
Discuss them further.
Yeah, so each coset is all the matrices with the same determinant. That was the conclusion. Does that ring a bell?
Don't they all have the same determinant?
Pardon?
Don't they all have the same determinant? Especially.
Yes, but no, yeah. So exactly. So one of the cosets is the subgroup itself, but that's always the case. And then there are infinitely many cosets, and each of the cosets is exactly the matrices with a given value of determinant. Okay. So each coset is the set of all 3 by 3 matrices with the same given value of determinant.
There's definitely some determinant.
So what happens if you do this?
No, I can't. Isn't that the order of both?
Yeah, so you get an infinite group, that's okay.
Oh,
There are infinite groups.
it's like if the world explodes, you just know how much. Trying to divide it.
Don't say it, man. You're playing
So
physics.
the elements are the cosets, right? So when you get one set of matrices, all have the same determinant x. Another set of matrices all have the same determinant y. And you do the product of these two cosets. Okay? You're supposed to get a coset. And you get the coset of, because it's a normal subgroup, you can pick any matrix in one coset and any matrix in the other coset, multiply them. And the coset of the result is the result of the multiplication of cosets. No matter which representative you pick, so no matter which matrix with determinant x you pick, no matter which matrix with determinant y you pick, you multiply them, the determinant of the result of the matrix multiplication is going to be x times y, as you know from linear. And so the result of the multiplication of cosets is going to be the coset of all matrices with determinant x times y. Now, if you take a mapping which takes this coset of all matrices with determinant x and assigns to it x, what is that going to be? Yeah, so you've got cosets as the element. Now, this coset is all matrices with the same determinant. So this coset you assign by a mapping x. And when you multiply two cosets, you get another coset, and the value of the determinant is going to be the product of the two values of the determinant. So what you're getting is an isomorphism of the factor group with the multiplicative group of the elements. Because these cosets multiply exactly as real numbers do, without zero. So this is isomorphic to R star, I think it's called. End of examples. How much time do we have? Oh, not so much. Section 10.2. Simplicity. Simplicity. It's a very promising title of a section. Of alternating.
Young prophets.
Groups.
It's simple. Yeah.
Sweet.
First, let's have a simple definition. Simple definition, which says that a group G is simple if
Every time we said that, I'll do it, but even very wise.
if it has no normal subgroups. Well, of course, every group has normal subgroups. So those don't count. So this is a simple group because you can't factor it in any way. Right? So the only way you can do a factor group is if you factor by this, well, you get G, nothing has changed. And if you factor by the whole G, you get the trivial group. Nothing, so that's not interesting. So simple, you can't really find any more complex structure within it. Permutations, you have a structure, odd, even. Here you have a structure, determinants, and things like that. Here you can't really find any sort of structure. And then there's some words and words and words, but let's skip to it. Okay, so the question is, are there any simple groups at all? And
Yes, 'cause it's-
I've already read it to the next line, so I know there is. It's great. Got next line.
so in fact, it was quite the first known simple groups that were non-abelian were found by Galois some time long ago, and then people wanted to classify all finite simple groups, just find all finite simple groups, and that was a very long-standing open question. Many people working on it, and sometime about, well, maybe in the late 20th century or beginning of this century, with huge books of text, algebraists finally agreed that they've probably proved that these are all, and there are no other finite simple groups, and they gave a list. And I'm not going to give you the list, but we'll just want to do the theorem that was by Galois, who proved that every alternating group on at least 5 elements is simple. So alternating is all the even permutations. And the proof is about 3 pages. So, but it's also a nice exercise in proofs in groups. So that's what we'll do today. We start today, and we finish it next week. And so let's start. It's got so this is what we're heading towards. And the idea of the proof is that the general idea is if you find a 3 cycle in a normal subgroup of AN, you can prove that the normal subgroup is the whole of AN. And then you show that there is always a 3 cycle in the normal subgroup. So let's get there. Let's just do one lemma today and the rest next week. The lemma is that if you take all the 3 cycles in AN, then subgroup that it generates is the whole of AN. Okay, so AN is generated by 3 cycles. If n is at least 3. While if n is 2, then you don't have any 3 cycles, so that's it. Okay. Should be doing this. Quick. It's really quite simple. So every element in n is the product of an even number of transpositions. Why? Yeah, that's the definition of AN. An even permutation has an even number of transpositions in it. Okay, so the product of 2 transpositions is one of the following 3 things. So it can be that the 2 transpositions are exactly the same transposition. So AB, AB. What do we get? The identity. Or it could be that they're disjoint. But if they're disjoint, you can in fact, so that's the tricky bit one, the tricky one. You can write it as the product of 2 3 cycles like this. Okay, so how do you check this? Okay, A goes to C, goes to B. A goes to C, goes to B. B goes to A, C goes to D, D goes to A, goes to C. So it works. And the last possibility is that they share one element. But then if you do the product, you find that this is A goes to C, and C goes to A goes to B, and B has to go to A. So that means that every element in the alternating group can be written as the product of some 3 cycles. That's it. End of proof of this lemma. And we will continue towards this goal, and that's really everything there is in section 10. On Friday, I would suggest we do some SAGE things following the book about normal subgroups, trying to show some ways and some things you can do in normal subgroups. So, any questions? All right. Hope to see you on Friday.
I need to show it on Friday.